Welcome, everybody, to the Leptoukh lecture this year. Hopefully there'll be more people dribbling in, though it is being recorded, I understand. I must admit, oh, he's not. That's true. It's 10:20.
Stop again.
Okay, well, in any case, my name is Ruth Doerr, and I'm your outgoing president for the Earth and Space Science Informatics Group. And Denise Hills is not here yet, but she's your incoming president. Hopefully she'll be here shortly. And then after her, it's Jeff DLB. So in 2 years, there he is, very good. And in 2 years, you'll have to think about who's coming up next. I think there's a lot of really great people in this section, which is a hard thing for me to say because it mostly was a focus group during my tenure. But please be thinking about the future. And on the subject of the future, I have to say that SE is about the most underrepresented section that exists in terms of AGU fellows and honors. We have Peter Fox as a full-fledged fellow. We have, as of this year, David Tarbotten as a split hydrology SE fellow. But that's it from fellows, and we really don't have a lot of other awards that people get nominated for. In the past, we've had good representation on the Falkenberg Award with people like Mark Parsons over there. Wow, shouldn't stand up in public and say anything. But there are a lot of awards and a lot of really important people in this community who have made extremely great strides in the data and informatics world in bringing the whole science enterprise forward. And we should be honoring them. So I note that about February is when all of these nominations are due. So you really should be thinking about it soon. I have some ideas myself. But for example, there is the Ambassador Award for Societal Impact and Service to Earth and Space Science Community. That seems like an obvious no-brainer. There's a lot of education, public outreach, et cetera type awards. The Flynn Award for Sustained Infrastructure. I already mentioned the Falkenberg and the Fellows, but there's a large number of awards. We're all eligible for pretty much all of them, and data activities count. So, if you know of somebody who's deserving, please nominate them. Thank you. And with that, I will turn it over to my colleague, Helen, who will introduce our winner of this year's Leptoukh Lecture Award.
He's looking really worried down there at the moment. Hi, good morning. I'm Helen Glose from the British Geological Survey, and I'm also the chair of the AGU SE Awards Committee. So I have the great pleasure today of introducing the recipient of the Leptoukh lecture. And I'm going to start just briefly by giving you some background around the award and to introduce our speaker today and to give his citation. So AGU's Leptoukh Award is awarded by the SE Division for an outstanding individual contribution to Earth and Space Science Informatics. It's actually named in honour of the late Greg Leptoukh. Greg was an earth scientist and an active member of the informatics community, and in fact there's been an excellent article published by Tom Narek. I don't know whether he's in the room. Oh, he's there. So if you don't know about the background to this award, please do take a look at Tom's article, which is quite comprehensive, and I learned quite a lot from that as well. But Greg was known for his leadership in linking science and technology for data analysis, data discovery, and multi-sensor data fusion. But I think quite critically, and Erin Robinson mentioned this in her talk earlier this week, he was noted for his vision of making data more readily accessible at a time when that was quite a new concept. The Leptoukh lecture itself highlights the role of informatics across the earth sciences, as well as the accomplishments of individual scientists. It aims to raise awareness of the often overlooked computational and data advances that enable breakthroughs in domain science, as well as fostering exceptional individuals to make continued contributions in informatics and data science. This year's recipient is Dr. Benjamin Evans. Sorry, Ben. He is Associate Director of Research Engagements and Initiatives at Australia's National Computational Infrastructure, which is hosted at the Australian National University in Canberra. Excuse me. Just to give you a little background around Ben. Excuse me, sorry. Ben gained his PhD in mathematical physics from the Australian National University, where he studied mathematical structure of space-time in Einstein's general theory of relativity, and please don't ask me to say that again. He subsequently went on to hold the position of head of the ANU supercomputing facility, and also led national programs in computational tools and techniques and the national data grid. Ben is currently responsible for NCI's innovation and development of future capabilities for HPC and data-driven science with their stakeholders at NCI, which includes research communities and national and international collaborators. His extensive experience over more than 20 years in the fields of HPC, data management, development of scientific computational and data software systems, and research management means he is well placed to steer NCI's involvement in a diverse range of national projects, such as the Australian Virtual Laboratories supporting climate and weather research, improving the performance of the Access model for Australia's climate and weather prediction system, which is carried out in cooperation with the Australian Bureau of Meteorology, CSIRO, and the ARC Centre of Excellence in Climate Extremes, and also the development of online satellite Earth observation services, which has resulted in Digital Earth Australia, and also the Copernicus Australasia Hub. Ben is also recognised for his innovative contributions to informatics, having published groundbreaking papers on high-performance data that focus on the use of analysis-ready data in the context of HPC. He's also highlighted the importance of community standards and their implementation in high-performance data to seamlessly integrate HPC and virtual laboratories, which have traditionally been quite separate. Ben's standing throughout the Earth and Space Science informatics community is evident from the various positions he currently holds on a wide range of international steering committees and working groups. These include the NSF's funded EarthCube Cyber Infrastructure Initiative and the Earth Systems Grid Federation, which underpins the international data fabric for climate simulations and observations that are ultimately used as part of the IPCC reports. Ben's proactive support of international collaboration across distributed communities has been a key element of his wider contribution to the ongoing development of informatics in the earth sciences. He has championed the increasingly broad community of practice in Australia and ensured that it is fully connected to similar activities around the world. And just to highlight this, for those of you who follow Ben on social media, you'll know that he can often be found sharing virtual pizza with his colleagues around the world following particularly productive phases of international collaboration. So it gives me great pleasure to introduce Ben to deliver this year's Leptoukh lecture, which is entitled Evolving Data-Driven Science, the Unprecedented Coherence of Big Data, HPC and Informatics, and Crossing the Next Chasms. Ben.
Cool. Good. Good. All right. Well, thanks very much, Helen, for that sort of history. It makes me feel like a bit of an epitaph, really. I wonder what I'm going to do next. But anyway, thanks very much to the Leptoukh committee for giving me this award and the chance to speak with you all today. And hopefully I've got something interesting to say about the journey that I've been on in this space, and also some of the challenges that are coming up. So, first of all, just again to highlight the legacy of Greg Leptoukh. Unfortunately, I missed Greg by about a year or so in my sort of first attendance at AGU, but I was very pleased that Tom had created this article in the EOS communication, and I put the link there. I'm not sure where these presentations go, but it'd be nice for people to have a look at that personal connection to Greg, and I think a lot of us can embrace the legacy that has been set up by Greg, and that's part of this award. The other thing is, on AGU, we're just approaching the centenary of AGU, so part of the mission for this talk was to think about a little bit of the past, and also to have a look at that future of discovery that's about to unfold. So who am I? Because I know some of you, I won't know all of you here, but I've gone through what is now, I think, a fairly standard sort of process in the modern age of various careers. So I did start as a mathematician and a physicist, specialising in general relativity, and I can still talk passionately about mundane items like partial differential equations and how to solve some of the complexities of all of these differential equations, the field equations of general relativity. But through various circumstances, there was opportunity and also constraints to sort of move across into a field that was just emerging at the time in sort of the mid-90s, which was supercomputing. So through various roles over about a decade, I led applications and sort of systems development. I then moved on to sort of be the manager of some of that national infrastructure, and then ultimately, as things evolved and things got even more sort of complicated and more people involved, moved on to deep science innovation and the research engagement side, which is really what brought me to AGU. You know, beforehand I'd be involved in technical conferences and a little bit of moonlighting in still mathematical conferences as well. But it's really the work that was going on in AGU that's brought me back each year to discuss it amongst colleagues that are working on sort of similar challenges. And I must admit, I wasn't finding sort of a similar cohort of people in any other settings apart from AGU and EGU in the SE group to do this. And part of the reason is because we work across all of the different domains, sort of picking up all sorts of threads. It's the only group that does that sort of cross-disciplinary, transdisciplinary in a very deep way to solve various problems. So I think there's a lot to thank the AGU and EGU for making sure that SE is still a success. Now, despite all this, I still class myself as a scientist. So that's sort of how it feels to me that I'm still in that sort of scientific world. But also, and I didn't put this on the slides, is I'm a manager of people now, and particularly younger people coming through and mentoring them. Really the journey that I was on when I started was like there was 8 of us, and one of that included the secretary, and we're all part of the team. Well, now it's a much bigger team, and really to get anything done, you've got to work internationally, and you've got to think of that next generation of people. So I'm particularly proud of that. And also I'd say we started off with a bunch of men basically, and now in my group at least, we're at least half women working on that. And not to say that was a quota, I think there's just a lot of good smart people coming through, and anyway, and I appreciate all of their input, as I do on the international field as well. So anyway, there's a few sort of slides there, starting with my general relativity and having a look at moving into computation. One of the reasons I got into computation, I should say, is because I couldn't solve anything anymore. I didn't know how to integrate. I was a pretty good mathematician, and when I got into general relativity, I couldn't integrate an equation. Nothing worked. And the reason for that is because general relativity is all about singularities. And when you're trying to solve anything around singularity, everything blows up everywhere, and no mathematical sort of construct seems to really help you. So I really got into it by necessity of this sort of computational field. And that sort of evolved, I guess, over time to do various things. Okay, so I work at this place called NCI in Australia. We've been tracking this sort of list of growth in computation. We started off with sort of some crazy vector machine single processors and working through into clusters and then finally to accelerators. So I've been tracking that now for many years. There's a well-known list called the top 500 list of supercomputers in the world. And you can see here, it might be hard to see the text, but the green line there, this is on a log scale graph, so it's an exponential growth and a log scale graph of machines, the total number of top 500 machines, the top machine in the world, and then the funny red squiggly line, which is the NCI systems, and a blue line, which is the bottom of the top 500. So we've been progressing along that, and there's been some challenges, which I'll talk about in a second, but that's been sort of fairly sort of straightforward in many regards. What has been more curious is data and storage and how that has rapidly changed really in this sort of period of time and the challenges gone along with it. So pre-1996, you were pretty lucky to store or retrieve any data at all. In fact, more lucky than might like to admit, but these hard drives here, which wasn't exactly what we had, but it's as close as my memory will allow, there was some hard drives in one of the government centres, and they were getting rid of them. And so my boss at the time said, okay, we need some hard drives, because we really didn't have any. So he put a bid in, but he was outbid by the scrap metal merchant. And so we were scratching our head. Anyway, he worked out who the scrap metal merchant was and sort of did a little deal behind the scenes. So we got some hard drives in, which was pretty exciting at the time, and connected it onto a machine. So it was actually pretty lucky to get these old washing machine style hard drives. But they've moved on over time, and we always struggled with our storage system compared to compute. Got into tape, HSM, and lots of data around that, and then finally around hard drive, sort of disk array sort of stuff. So that was really what happened until about 2005. It was quite a struggle. And at that point in time, we got things, better online storage. So Lustre file systems started to emerge, but also the demand for data really skyrocketed. And just on the right-hand side there, I've just plotted our compute compared to storage and online storage. And you can see from about 2005, and this wasn't just to do with infrastructure being available, it had to be there, but the demand to have storage available online and near compute really skyrocketed, and that hasn't abated. Really, and so in fact there's a lot of communication now in the HPC side to say, well, we're not cycles limited, we are cycles limited, but we might be storage limited before we're cycle limited. So I'm going to talk about that trend. We've also had the rapid growth of analysis environments. So about 2009, we had our first installations of cloud, starting with sort of VMware bits and pieces, and then OpenStack Cloud put together. So these were some diagrams at the time of infrastructure going in place. But about 2013, and this was part of the switch, I think that was the end for me of systems and how they really worked at that layer, and I really moved into this sort of software layer. And that's where we started to be able to deploy these worldwide accessible data services like in astronomy. They were the first that we went through, IVOA, and also the Earth System Grid Federation for the climate analysis at the time. So, beforehand we used to ship hard drives around into the centres, and that became infeasible as we moved into the CMIP couple modelled in the comparison world. So we started getting involved in this crazy experiment called the Earth System Grid Federation to try and federate these massive online infrastructures where the climate models were being generated. 2013 to 14, we really put online just various systems to make it easier for people to get a hold of data. So both interactively sort of logging into things and also through data services, just to make it more frictionless. Now, the growth of data collections or data in general, not sort of much data collections, but the growth of data is sort of well known. And IDC does just various industry trend analyses, and it says that the information's doubling more than doubling every 2 years is their estimation, so somewhere around 30 zettabytes in 2018. But more importantly, they said the number of files is growing even faster than the storage capacity, and that's something I want to touch on. So in the next year, these files will grow by a factor of 8 over the next 5 years. The other disturbing factor, but I think is true about sort of scalable systems, is the pool of what they're calling IT staff. They are, after all, a sort of an IT sort of organisation, but IT staff who manage them will only grow slightly. And that's the challenge that we've got of how to meet that scalability demand. That's the thing that we've got to keep an eye on for the future. So our trends at NCI, so we did some of this tracking as well as other centres. So the data collections capacity is doubling every 2 years. Scientific data sets are growing even faster, 3 times over the last couple of years. We've got about 310 million files on in our storage systems. And the request for international data is growing slightly faster than the domestic, but both are working exponentially. So that's the demand in front of us. That's a log curve again. So it's great doing log curves. You can draw straight lines on things and start to predict where things are going. The constraint being more, I think, costs, which I'll get to at some point. So the way I think about data is, I guess, goes back to why do I want to store some data near a HPC facility? And the answer to that is because we've got to do computation on it. Otherwise, I just don't have a reason for doing it. So I'm pretty single-minded about the ways to think about data, and that has to be organised for computation. And I equate this to how the printing press revolutionised the written language. And that is that, you know, they started doing sort of putting machines in place. The printing presses started off with plates, whole plates, and it was a bit sort of cumbersome, but the real change was as they got into the detail of just doing these movable type and using metal movable type. And it was the machine's sort of veracity on being able to pump this stuff out and reproduce it and sort of easily share across different printing presses that really straightened out all sorts of things. Like, not only was it a speed issue, but it straightened out the English language. A lot of the funny characters disappeared. You know, the thorn disappeared as a part of this. Funny spellings disappeared because it wasn't the person who chiselled, you know, on the plate, which was a cumbersome exercise. It was the movable type that straightened all of this stuff out. And it's just that veracity of the machines to help straighten out these sort of fundamental parts of the world. So I say that similarly now we're going through this for data, and what does it mean by data? And if it's to make it sort of computationally accessible, then we're on a really good pathway. All right, so on that first slide, I'll show you the top 500 list. You'll notice that things were sort of tipping over at the top. And when I showed this to Leslie, she goes, "Oh, can you explain, why that is?" So in the sort of IT industry, and I think it's more of an IT industry, they talk about laws. Okay, so I thought I might go through a few laws and see how many you know. I think some of them you will, and Moore's law's been pretty well celebrated, that the transistor density doubles every 2 years. So that was going pretty well. In fact, he did revise it in about 1973. It used to be every year, and then he sort of went, it's every 2 years, and that still fitted the line. So that held for a long period of time, but it was busted in 2012, and it really was. Just hit the limits. Okay, let's go for a few more laws, see if anyone can see how they're going. So the top 500, HPL, well, I showed that before. Increase in performance about 1.85 per year, and unfortunately that one broke as well in 2013. Actually, it was partially as a consequence of Moore's law, but there's a few other ones. There's a thing called Moore's second law, which says about sort of cost of production of these chips as well, that plays into the economics of this. Another one's called Dennard Scaling. It's got a little bit more complicated sort of description around it, and it says as transistors get smaller, circuitry gets faster, and their power density stays about constant. So power use is proportional to area, and that you can sort of equate that to you buy a machine and it's using sort of the same amount of power inside of it. But you notice for a while that the clock frequencies were going up and up and up, and then at some point that one got busted as well. And no more clock frequency increases. That's the circuitry getting faster. So instead there was more cores on the die. So Dennard Scaling is one of these ones that's driving a software change as well. To get the extra performance people need, you need to go more and more parallel. So these are, anyway, so that's Dennard Scaling. Kumi's law, power per watt, doubles every 1.57 years. So that one broke in 2005 after many years of being correct. Kreider's law, areal density of disk doubles every 13 months. So that one was looking pretty good until the point that the paper was published in 2002, and then it broke straight away. So not looking real good for these apparent laws that we've been on. How about this one? You might know this one. Worth's law, software is getting slower more rapidly than hardware becomes faster. This one was equated to what Intel giveth, Gates takes away. You heard that one? So anyway, I say, yep, that one's still in pretty good shape at the moment. And the question is, can we break this one? And I think that's the challenge before us. And here's my favourite, Parkinson's law, which says work expands so as to fill the time available for its completion. It's the analogue of the ideal gas law. So I think that one's going pretty well. So the only thing that we can do there to meet that challenge is to set goals and go for the highest quality. That's my mantra on all of these things. Just go for high quality, and that's the best you can do. All right, why do we build shared HPC and data repositories? This is sort of more of a motivation of where we've been at. So at NCI, we're a national facility, and really there's a whole lot of data collections around that had to be pulled together from different organisations. And you can see there's sort of a mottled graph of, you know, where data came from, and they overlap in different ways. And the idea was, can we make this better analysable if we stick it all together in a big shared facility, a big national facility, and really a computational sort of aspects around it. So the focus on these collections to make it high performance. It gave us the ability to do transdisciplinary science, mostly in the geoscience domain, but I don't think you could find a geoscientist in one field or another who don't think they're special. So the challenge for SE sort of community is always to expand that horizon. It's a lot about the integrity of the data inside of that. That's our challenge. And also what I'd called at one point in time the IQ score, because I heard about smart data and I thought, oh yeah, what's that mean? So I sort of created this label, IQ, which is the impact and quality. And they're the things that matter for me, impact and quality. That's got to be it. All right, so in our area, we're working on priority research and societal issues requiring this world-class HPC, and there's a number of things driving us there in our particular community. I mean, there's other things going on inside the facility as well, but the particular drive is, can we solve this sort of grand challenge set of problems in front of us across these different domains? So what we've done is integrate these HPC and data-intensive science capabilities together and see if we can't make sort of this holistic sort of view work from machine-connected things to compute-intensive. The other thing is, to make all of this high performance, it's got to work both in big compute and also for big data analysis, so people can pierce through time very quickly to analyse in a big time series or, you know, across different parts of that domain. As we've done that, part of the challenge has been, can we make long-tail data easily analysable next to that big, large reference data? And there's various techniques, and maybe I'll go through some of them to give an indication of that. Of course, I can't put all of these details in the slides or talk about them, but I'm very happy if people want to talk about, well, how's this go? But one example of where this has come out is, for us, there's a visualisation. It's not quite released yet, so if I slip my finger, I could make this work, but it's all being recorded, so I can't do it. But anyway, it shows models sitting next to observational data over a long period of time and sort of showing how these exactly equate. And it's a very powerful sort of example, really, of pulling all of these different types of data together and how they interplay. And it's beyond really what the science can do. You know, we're really relying on other tools, visualisation tools, and sort of this interoperability of data to see these things that are impossible to see otherwise. So if anyone wants to see me later to get a little preview of something not quite released, I'm happy to show you that. exercise. So what's driving the big data? It's climate and weather model data, reanalysis data, and the observations. They're the big drivers for us. There's a few new areas, genomics and whatever, coming in as well. I won't want to talk about that too much because it's still a work in progress, but the fundamentals of these three areas really are driving a lot of activity. All right, next part, striving for better quality and ongoing scalability and data management. So had various names for data management plans. Today I'm talking about mischief managed, a la Harry Potter. And it's the question of how to get these responsibilities of data between different organisations and stewards and owners, and how to put that into sort of a proper case for why it exists in the first place. Making sure that it's versioned, getting the quality up. And it takes a big community exercise really just to make that happen. In particular for tracking use cases and impact measures and user training examples. So a problem we all know well, a problem for scalability is most of the time is spent just cleaning and organising data. So 12% prepared for, I think it says there 60%, really you spend on the preparation of data, and there's only 9% left for the mining of that data. And really this is beyond any particular researcher to be able to do that preparation. It's very complex sort of systems we need in the informatics world to make this work. And so the challenge, I think, as a community is to provide that really solid basis that more discovery can happen on top. On data quality, we wrote a paper just on our strategy for how to do that, which really says there's no one standard that actually tells you that you're going to have good quality around your data, in particular around the usability of that data and through all of the applications and data service layers. And so something that we put in place for ourselves is to make sure that we took a whole bunch of examples of how data should be used by different domains and making sure that everything worked before we put it out the door, or at least know where it broke, and then could come back and sort of fix it up as we got better at maturing these things. As part of that is performance measures. As Helen mentioned at the start, we sort of did this definition about high performance data, and that is data that is carefully prepared and standardised and structured so that it can be used in data intensive science. It wasn't just collect some stuff and store it, it was to really take it to the next level. HPC is often talked about as turning compute into IO bound problems, and so by doing this HPD we're turning the IO bound problems into a data analysis opportunity. In terms of working through this, a very complicated sort of stack of sort of measures and whatever, and you'll be familiar with them. I'm just saying that putting in place sort of baselines and understanding why you're putting data in place is a very important part of preparing for that scalability. For FAIR, I wasn't going to bore you just by putting up the full description of FAIR, but one of the problems for right now in FAIR is that there's nothing about how you access the data through a service as part of that. It's not an API-ish sort of world, it's just about putting some data out there. It's almost data download driven. So one of the challenges for FAIR is now to put on other things, which is how do I connect to the data? And there's data services in the road of that, and there's information systems on top of the data. So there's a few things there. I won't go through them now about what needs to happen around that. Pretty much they just come down to making sure you've got real accessible APIs that a program can use. Learning how to be trustworthy. So this is a major challenge for us all, I think. If someone gave you their digital science output, what would be needed? What do you need to be convinced that it was correct? If it's a complex system that you couldn't run yourself, what assurances do you need? How much should you rely on these results over the longer term? So these are really challenging problems for us. And the Core Trust Seal is part of that measure. I think we'll be hearing a lot more about the evolution of trustworthy science. One of the issues in this area is just knowing what we mean. So one is about what's reproducibility, what's repeatability, what's replicability. And so there's definitions of this that the ACM, the Association for Computing Machinery, have put out, and it comes from a vocabulary of metrology as well. So these go to, is it the same team with the same experimental setup that can do repeatability? Replicating something is a different team on the same experimental setup, and reproducibility producing it is a different team with a different experimental setup. Now, these are really big challenges, and in fact, I've gone through this in a fair bit of detail, and getting repeatability in place is challenging enough, and the rest of it is actually very, very difficult. So I think this challenge will be with us for quite some time. So what do we need at scale? If it's not feasible or practical to do all of this, what do we need to gain trust? And a lot of it's about transparency, and that's an informatics issue for us, about how do we record and in what should we record and how do we represent that as well. And the bigger challenge is then make that a computationally accessible part of the infrastructure as well. So we've got quite a bit to climb, I think, around this one. Do we hand out our unit tests and scenarios and procedures? How or should we record and share the level of variability or precision that is in the data? How do you put it into auditable systems so that people can't just cherry pick results? Do the system maintainers even understand their underlying system, let alone you? Does anyone know the versions of their big and unique systems? Anyone care to know what the version of Amazon is today or tomorrow or a month ago? You've got no hope, really. So it's, understanding the experimental infrastructure you're working on is very hard. So transparency is supported by FAIR principles, but it really needs to be promoted much more broadly than data. It's only one part of the whole puzzle, and the software is certainly a part of that. And in fact, Simon Hodgson, I think, just released some articles. I'm not sure where it came from, but let me just say through the CoData initiative that talked about the need for other FAIR principles to be applied to digital objects. Okay, and if any of this is science, we need to do this, right? So this is a big challenge in front of us. This is not going away, and I think it should be one of the things that drive us. But in more emerging issues is, to what extent should we put information around uncertainty and sensitivity when we get to things like trusting deep learning results, machine learning and AI? I think that's quite a challenging one at the moment. The best that we hear sometimes of deep learning is, well, maybe it's 90% accurate. I don't know what that means. So, these are emerging areas that we're going to have to get on top of. How do we look at workflow system and microservices? Is this where we're going to start seeing blockchains play a role in this and putting PIDs around blockchains so that we can sort of certify what's going on? And to what extent do we expect provenance records to be available and usable in any meaningful form? So that it's a long way to go in provenance world at the moment. I'm sure we're happy if we just get a record, but really there's a long way to go on what that means. The other thing is to check any conclusions for the data in different ways. So there's this thing called Enstrom's quartet that was released in 1973, and it showed 4 graphs of the same meaning, same mean for some statistics, same variance and correlation, but quantitatively different. And then it was updated more recently by these people, Justin Maytekia and George Fitzmaurice. It says same stats, different data, and it's called the Datasaurus dozen. And what it showed is that they could produce almost any data and produce, show the same results on this. So, and within 2 decimal places. In fact, as these things sort of transition around, within the first 2 decimal places, all of these transitions show those same key variables. So the question is, when you're working through all of this data, you've really got to check it in multiple ways. And I think it's one of the things to make sure it's in the hands of other people as well and not just yourself. So. Virtual laboratories, or what we sometimes say is, how good's my stovepipe? And we see a lot of it, and we're all responsible for this because we're really trying to get a science problem solved. But we're really expecting a bit too much of the data in some of this. That is, you've got a whole bunch of different communities trying to attach on to the data underneath, and it really does not have much hope of sort of solving this problem. Everyone wants to transform the data into their particular form and their legacy and whatever. So just putting a bit of a catalogue system and expecting all of these things to tap into the data is too much to ask of the data itself. And what, of course, there is out there is different data services and standards to help get into that. So one of the things that we've been doing in NCI is to provide better high-performance data services. So one of the things is, how do we attack this problem of lots more data files being around, and who really wants to deal with data files anyway? Currently we've got over 300 million. By 2020 we're going to have 1 billion data files. Do we really expect a researcher to attach onto 1 billion data files and mine it for any information? So we've put in place, as others have as well, a way of harvesting that data and making that searchable much more easily, and then putting some services over the top and servers over the top of that and make it fast. POSIX file systems way not keeping up with this, and neither are really some of the cloud infrastructures, and they're not going to keep up with this. It needs other parts of infrastructure to make it work. Another barrier is, do you like my coordinate system? As I said, everyone wants data in their particular way of representing things, and it's just impossible to do some of that without thinking of data services transforming on the fly. So we tried a few years ago to see if it's possible. It's a little challenge for ourselves. Can we just computationally on the fly transform data to the coordinate systems that are that are needed, stitching it together? This was Landsat, Himawari, and some ERA data, just transforming it on the fly and make it usable. And from that, we've now set up a service that does this. It's an OGC compliant service, or near compliant, for how do you transform this data using WMS and WCS, which is a way of getting to data, and then putting WPS services on the top as well. So there's a scalable infrastructure. It's got to be next to the HPC. It's got to be near the compute, but you want thin clients that people can attach on to this data. So now we're increasing the number of, especially Earth observation data sets, to make that accessible and very easily, without the user knowing of anything about files or all of that sort of junk or anything to do with HPC or scalability. They just ask a question of the service in a standard way they would ask before, and then the hard work is done at the back end and serve up the results in real time. So there's a nice write-up of the work that we've done on this URL that hopefully people will be able to find. So what's the value of the data? And this is where the challenges are coming in. So the business model around data repositories is tough going. And there's a nice sort of capture through this report that took a couple of years to come out from the OECD. But one of the issues around this is that this generalised Parkinson's law, and that is that demand upon a resource tends to expand to match the supply of the resource if the price is zero. Right, so it just fills the space. Doesn't matter what you're doing, it'll just fill it. But the reverse isn't true. So the resources don't expand to meet the demand, and that's the challenge for the business models. Next question is, how do we measure the value of this work? There's a part of the ecosystem that the data infrastructure plays, a really important part, and we've got to keep attacking that and understanding that quality measure and how to report on that work. So this is a whole research sort of data cycle all the way out to outcomes and impacts, but it takes many years for that to really be known. But there's a component of this that we can work upon and keep on sort of tracking the more historical data on the outside. So that includes being able to track, well, what we call the data crater, what's the size of the impact, tracking usage statistics, who's using, always sort of answering the political questions that emerge as that data is more used, or it should be moved aside for something else of a higher priority. Tracking research data footprints has become now possible through things like this research graph infrastructure. So how do we connect on to who generated the data through to publications? And that's a big graph network that really needs to be generated. Now there's a working group inside of RDA helping to work on that. Attaches into things like our catalogue services, making sure all these persistent URIs and sort of persistent identifiers are working on the data, and then mixing it in with all sorts of other data that are out there through ORCID and DataCite and whatever, to create a better map and a better understanding of what really is that impact of data. In terms of, I'm up to the last couple of slides. So in terms of increasing some productivity, there's a lot of human factors to overcome. And in some sense, the research community is sort of helpful, but we also try to work increasingly across into the industrial sort of space as well, and sort of, starting to chat with communities there. And one of the issues there is just moving from this personalised fame to shared assets, so that you get a more productive future out of this. And it's quite a challenging human problem, removing barriers to stop the progress and slowing the productivity, and replacing sort of unscrutinised way of organising data and moving it into standards and interoperability and trusted processes. Lessons relearning, after a certain size, you really need to get to some sort of common platform. No matter what you're on, you need to get to that sort of system scalability, not a people scalability problem, and continue to address the challenge of working across the different domains. So before I get to my last slide, there's a lot of people who've been working on this stuff, with me and in collaboration with us. So I haven't listed everyone here, but just to say, I've been working on this now for some period of time, really a sort of a culmination of 20 years or so, to pull these things together, and it wouldn't happen really without the collaborative activity and new people coming through and new energies sort of getting into this. So this is my summary slide. What do we do for preparing for the next discovery? And then we've got the rapid convergence of issues of scientific tolerance, being transparent on all of these infrastructures, robust software deployment, and even more integrated information systems, preparing and transitioning to the next generation of that hardware that's coming out, continuing to understand the nature of the business model. More investment in building software is now the real key. And also growing the people at the same time. I should say there's hardly an advertisement for a position that I pull out that people don't have the right skills for, and it's a matter of growing those people through this very unique sort of ecosystem that we're in. And the other thing is people just do not scale, and systems do. And so that's the sort of drive for us to make sure that we keep on pushing into and improving our systems, because that's the only way that we're going to prepare for the next generation of discovery, which is in the hyperscale and the exascale world. My last little bit in the corner there is, riding the Gartner curve of hype. I must say, I've looked at these Gartner curves and I can't make head and tail of them most of the time. They've never provided any particular insights to me, but I know that we're all over that map, and particularly we're on the right-hand side. Anywhere from that trough of disillusionment and through to the productivity is really where we play, quite a lot. And there's a lot of hard work in doing that, but I know that we are all over that map because deep learning is on the peaking up sort of side of that scale, and there's been some really impressive talks here at AGU this year. And I think that's the end of my talk, so thanks very much for listening. I'm happy to take some questions.
Okay, thank you, Ben. That was great. So do we have some questions for Ben? Yeah, please. Yeah.
Well, first of all, thank you very much for a great talk. Learned a lot, honestly. But my question is more about this exponential growth types of curves, and it seems like as a community we've committed to let's put all the data online, and we're going to just always be finding more RAID and find more money to buy cloud resources, things like that. That feels very fragile to me, and I'm wondering if there's any thought about a plan B to that. I'm thinking maybe of is there any immediate solution that could ever keep up with an exponential growth of data without an exponential increase in funding?
Yeah, it's a good question. Could I repeat the question? The question was, is there any magic storage out there that can help with this data growth? I think that's sort of the fundamentals of it. Sorry, I really don't have the answer to this one, and I think it's a sort of a challenge upon us. There is a lot of going on with federations so that we're not sort of unnecessarily replicating data that's not required. So that's part of it. I think there's a lot of junk around as well, to be honest, as we go through this data that can be stripped away and sort of get the higher value of the data. But other than that, I think that just the challenge is upon us, to show the value of that data, and as the dollars get smaller, or not smaller, but the pressure on the dollars, become more real, then you've got to know what the value of that data is. Otherwise, it will just disappear. There won't be the funding stream for it. So I can't quite answer your question, fully. People do data more than just on big platforms as well. They're working in that space, but really you need the big systems for that sort of shareability, I think.
So I think Peter Fox has a question.
Nice try, man.
Thanks, Peter. Heckler.
Yeah, I had to have one. So for the people in the Northern Hemisphere, could you maybe make a few comments about what the Australian overall approach is to providing national infrastructure like you demonstrated very clearly over a period of time? Because I would argue that the United States, but even the European Union, have not necessarily had this sort of cohesion and agility. And I personally, I've asked you this question before, the audience might like to know a little bit about the will that you've had to go and do a lot of these things.
Yeah, thanks, Peter. It's a good question. Our funding regime's pretty poor as well, like other places as well. But it does take a bit of vision, I think, to sort of pull a lot of this data together and make it sort of workable. I don't think there's an overlying sort of an overarching strategy that governments sort of understand of how to put this together. But I think a lot of this does come down to people as well, with a bit of vision, a scientific vision and technical vision on sort of making this a sort of a better way of going. I have noticed a lot when I go to the HPC conferences, which really do have a lot of big money associated with it. I am sort of surprised still that the HPC community in general doesn't quite get data at all. I have to say that's pretty much my experience. And I went to SE, not this year, but last year, and I was surprised that people only want to talk about methods, not about the data and the accessibility on that. So I think there's a road to go there through those communities on how to work. I don't really have a magic answer to your question, Peter, I must say, because I feel it's still a struggle. But I think some of the things that we've done, System Grid Federation and data services and whatever in general, are showing a component of this that works. I think that the biggest problem that I feel at the moment is if the data is just sucked into HPC facilities or stuffed inside of a so-called public cloud, or commercial cloud, putting all of the data in there and not allowing it to be accessible in other ways, I think would be a travesty. And so you can see, I've been unusual, I guess, at one level in the HPC area to make sure that we always put data services on there and think about computation outside as well as inside of the domain. So I think that has proven a little unusual, not uniquely so across this community, but I think more generally, I think that is a bit unusual in the way things have gone. And from my point of view, because the clients are thin out there in the space, so computing on the edge is where it's all happening. We talk about big data in the centre, but really there's only I've heard the number, 20% of the data is in the inside and 80% of it's on the outside. And if we looked at the growth curves of various things of where the data actually is, and with people, it's all on the outside, it's not on the inside. And so making it interoperable with these reference data and what's going on outside is a really important part of that ecosystem. So I think that's sort of a bit of a challenge in front of us. I've talked about that before with fog computing and a few other things, and whatever you will like to call it, this computing on the edge is going to be a factor of our lives for sure.
Okay, well I think in the interest of time, I'm afraid if anybody else has got questions for Ben, I think you'll hear
around.
So he'll be around, so please do feel free. So Ruth, I think you're in charge of the...
Yes. So, Ben, very nice.
Thank you. I thought it was just a piece of paper.
No, you actually get a little glass thing that you just...
There you go. It's even got my full name, which I only get called it when I'm in trouble, generally. So.
Right. And it comes along with a nice...
Very good.
But you have to come down and we have to take pictures.
Oh, okay. All right. Well, thanks everyone for coming along. Much appreciated.